Good morning. My name's Kat Megas, and I'm with the Trusted Identities Group. Some of you may not be familiar with the title Trusted Identities Group. We were formerly known as NSTIC. We were the National Program Office for the National Strategy for Trusted Identities in Cyberspace. And recently we went through a transformation, and we are now the Trusted Identities Group. So we have a pilot program over the last 4 or 5 years. We have put out about 22 cooperative agreements to private industry with the purpose of seeding the marketplace with solutions that are trusted. And by trusted, we mean privacy enhancing, secure, interoperable, and easy to use. Under this program, we have a couple of pilots, and one of them is going to be speaking to you today. And in particular, I'm interested in this pilot as well because in addition to my Trusted Identities hat, I'm also the NIST IoT Security Program Manager. And the Galois project represents probably the cross-section of both securing the IoT, securing the data around the IoT devices, and obviously authenticating people with strong authentication mechanisms. So, nothing more to really say. I just wanted to introduce Isaac. Thank you.
Thank you, Kat. Good morning, everyone. Let me pull up my slides here. Happy Monday. Okay, so as Kat mentioned, my name is Isaac. I'm going to talk about IoT and identity with a little bit of a focus on why the world needs better dev tools. So a very brief background on us. We are a product company focused on authentication, user and device authentication, as well as secure data storage and sharing. Primarily focused on serving the US federal government, a lot of experience here with NIST, with DARPA, DoD, and DHS. And we're actually launching a commercial product on July 11th, focused on this work. So very, very excited. We're going to be hopefully getting a lot more focus on commercial. We were founded in 2013. As Galois mentioned, we're partnered with a company called Galois, who's actually our parent company, and I was with Galois for about 10 years before founding Tozny. Galois is a research and development company focused on cybersecurity. Is the audio okay? Here's a little echoey to me, but if it's okay to you guys, I'm good to go. Okay. Kat mentioned we are partnered with the Trusted Identities Group. NIST is working to promote best practices for security and privacy, and we're one of the pilot programs to build privacy-preserving technologies. And we're one of the first companies to build a product from the ground up using NIST's Privacy Risk Framework, the PRAM. And I'll touch a bit on that in our talk here today. So our basic thesis is that most security and privacy challenges actually stem from a lack of good tool support for computer programmers, for software developers. So in a couple of little instances, this talk will get a little bit nerdy because I'm a computer programmer, but I will hold your hand. There shouldn't be anything in here that doesn't make sense to everybody in the room, so this should be completely understandable to everybody. But if something doesn't make sense, it's a fairly small crowd, so shout out a question if you want, and we'll just handle it real time. If we get too many questions, we'll just handle time that way. The other aspect of this, besides focus on developers, is a focus on cryptography. And that's because crypto is really everywhere. It's really the foundation for security and privacy in so many instances for identity, for privacy, for IoT, on the mobile, on the web. And developers very, very often get crypto wrong because of a lack of good tool support. So I'll have a few instances of that in my talk, a little bit of the work we're doing to try and address that issue with the support of NIST, and a bit of exposure to how we brought the privacy risk framework that NIST developed into our work. All right, so diving right in. Let's talk a little bit about IoT. Now, everybody has a different opinion about exactly what IoT is, so I'll say this with a very rough consensus with the understanding that everyone in this room will slightly disagree with something I say in here, but you have to start somewhere with IoT. So my definition is that there's a lot of devices. Many are low-powered, and they sense or they control things. Now, in the consumer space, this means it could be smart home devices that are monitoring things throughout your house, wearable devices, transportation like smart vehicles. On the industrial side, you have SCADA systems, which control industrial equipment. You have heating and cooling systems. And on the healthcare side, there are lots of new medical devices coming out. There are fitness bands for the consumer market. So IoT is kind of all over the place and supporting a lot of different use cases. What's challenging and different about IoT? Again, not every IoT device has these challenges, but here's the very rough concept. IoT devices tend to be fairly low powered. That means they are usually relatively cheap devices. They often have batteries, and those batteries need to last a long time without a lot of intervention. That really impacts, going back to the crypto side, that really impacts the strength of cryptography that you can provide in these devices in many instances, and it impacts the type of network connectivity that these devices can have. They might not be powerful enough to spray Wi-Fi. Oftentimes they're large scale. You have lots of devices. They're distributed by many different manufacturers, and this makes key distribution to these devices really complicated. It's hard to get crypto keys, unique crypto keys, onto each device when you're producing millions of them. And there's a lack of user interfaces in many instances. They don't have screens, they don't have keyboards, they don't have buttons. So how do you authenticate these things? How do you use any kind of knowledge base or challenge response based authentication to interact with these types of devices when you're pairing them onto a network or when you're just trying to understand whether you can trust the signals coming off of them? And finally, probably the scariest thing is that in many cases, they just don't get security updates. That could be for many reasons. That could be just because they were rushed to market without a plan for giving them security updates. It might be because they are generally disconnected from the internet and there's really no smart way to push security updates to them. Or they could be something that just cannot go offline randomly, shut down and reboot in order to patch themselves. They might be some kind of critical system that you just can't turn off and turn back on. So if you know much about computer security, you may know that software updates or the lack of software updates are one of the worst things in computer security because known exploits get out there and people use automated tools or targeted tools to just really, really easily exploit systems because they can download something off the internet that says, I know how to exploit this system. So security patches are one of the most important things. IoT is often very challenged in that space. The other thing is IoT risk is a little hard to define. And this can vary with security risk and privacy risk. So mostly I'm going to talk about security risk here. But some IoT devices have very low or moderate risk. Smart home devices, you're turning on and off your coffee pot, your fitness band maybe doesn't work or track your steps. Entertainment systems aren't working right. These aren't high-risk security devices. Now, flip that around to privacy, and these are actually high-risk privacy instances. So a fitness band that tracks everything you do has almost no security impact, perhaps, but it has a really, really high privacy impact because it's sharing information about you with potentially unknown third parties. On the other hand, some IoT devices have a very high security risk. They have life and death consequences for these devices to operate as they're supposed to operate. And those are, of course, especially in the medical or SCADA systems. Anything controlling the physical universe has a really high impact if you can change the way it operates, or if an attacker can change the way it operates. So it's also really challenging to understand how these devices might interface with an environment of other devices. The motion sensor that you buy in the store and you install in your house to turn on and off your coffee pot when you wake up in the morning is the same motion sensor that your neighbor uses to trigger an alarm system when someone walks into their house. So one of these is a security critical application, one of them is not a security critical application. These things are marketed in both ways, and how do we think about the level of security and, for instance, the cryptographic pairing that happens with these things? If an attacker can connect to your wireless motion sensor and turn it off in order to walk into your house, is that a security vulnerability? And then you have kind of blurred lines, again, when you interface these systems. So your car entertainment system might not actually be as segregated from your brakes as you wish it was. And this has been shown a number of times that you can attack or have in the past been able to attack vehicle operating systems from non-critical systems like the entertainment system. All right, so I mentioned I was going to focus a bit on crypto. So let me talk just for a minute about this cryptographic algorithm AES, because I'm going to use it as an example a number of times. It's actually my favorite cryptographic algorithm. I hope you all have a favorite cryptographic algorithm. This one's mine, and it's also my favorite one to pick on. So I'm just going to explain AES in 30 seconds so that we can all be on the same page. It's a cryptographic algorithm, so it's very close to the math. It's used everywhere. There's very few systems that use cryptography that don't use AES. Now, that's not to say you can't get around not using AES, you can, but AES is really, really everywhere. It's very fast, it's very efficient, it's been optimized for hardware, it's been around for many years. Critically speaking, it looks really easy to use, and there's a picture of kind of the way it works over there, but it's not really easy to use. It has a lot of different, what we call modes of operation, a lot of different parameters, key sizes, and different things that tweak the way AES works, and that can actually make it extremely secure as you could ever possibly really need, or absolutely insecure. Just depends on how you use it. And this is just a depiction of it happens to be a fairly insecure way of using AES, but just to kind of show what a cryptographic algorithm is, you input the plain text on the top there, you have a key, you have the algorithm, the block cipher encryption, that little thing, and then the other end you get the ciphertext. So that's all you need to know about AES. A little bit back over to IoT. So I'm going to talk through an example challenge from a government project that we had to try to illustrate and tie together these points about crypto, dev tools, and IoT. So what we had to do was we had to develop a very lightweight device that was proving its identity to either a network or another machine. So this is machine-to-machine identity. What is this device? Is it authorized to be on the network? Is it authorized to do what it's trying to do? So what we needed was a cryptographically strong challenge response authentication system. And we know that there are many of those, like OAuth and many others, that do these kind of things. But we had a lot of constraints. We had super tiny chips, very, very, very tiny chips, very, very low power, and no network. So the use case, again, is identifying devices over the network. Since we didn't have a network, we relayed stuff via the mobile device. And this has a privacy impact if you have unauthorized devices on the network, and a safety impact if you have counterfeit devices operating in sensitive equipment. So that's a little bit about the framework there. So there wasn't anything off the shelf that we could just pick up and use here. There was an obvious solution that we found that fit these constraints. It was pretty perfect, but it was very non-obvious. And we had to do a lot of work to get this system to work. It's just called AES synthetic initialization vector, which you don't need to know, but that was the solution we found here. And let me talk a little bit about the kind of heavy lifting we had to do to make this work. We had to choose an AES mode. We had to explain it to a cross-functional team in hardware, software, and networking. We had to define a new binary identity protocol. We couldn't pick up an off-the-shelf protocol like OAuth or the kinds of things that this conference is all about. The team we were working with actually had to construct the hardware. They could use AES off the shelf, but they couldn't just use it exactly the way it was. It had to be customized. And we had to construct the software network and relay protocol. This mode of AES is not very widely deployed. So this is just an instance of a very lightweight IoT project, but most organizations really aren't in a position to try this hard to get it right. And that's what's so challenging here. Why was this hard? Because developer tools for security and privacy are very, very weak, particularly in cryptography. But this challenge is not just about lightweight devices like I'm pointing to. Linux and Android are very widely used in IoT, but this situation for computer programmers trying to get their job done isn't that much better when it comes to cryptography. So if I'm a computer programmer, I have to sit down, write a piece of software for an IoT device that might be running Linux service, and I have a lot of the power of Linux in my hand. What am I going to do? I know I need something secure, so I look at the documentation for Java's crypto system and say, hey, how do I use this thing? So here's a little example of the crypto libraries in Java that you use for Android. If you were an IoT programmer, this is what you'd see. You don't necessarily need to understand this, but what you should know is that there's almost no actual information in this documentation here about how the system works when a programmer sits down to use it. If you do happen to know Java, you'll see at the bottom of this throws clause. And the funny thing about this is you can tell there's more information about what might go wrong. That's what throws mean. There's more information about what might go wrong with this algorithm than what it actually does for anybody trying to use it. And this has been so widely deployed. This is like the most common cryptographic system in Java and Android all over the place. So a developer comes here and just has no idea what to do with this. There's just no information here. So what's the second thing they do after they try to do the right thing? They look at the docs. Then the second thing they do is they Google for it. So we did a Google search for Android. We searched for encrypting strings in Android, which you'd think would be a pretty straightforward thing. Really, honestly speaking, 9 out of 10 or N-1 of the top front page of Google for how to do this was absolutely wrong and insecure. It was what I like to call the worst crypto on the internet. So and there's just these 2 lines of code here, which again, you don't need to understand what these lines do, but the get instance function at the bottom is the one I was showing you from the previous slide. And the impact of trusting this code that somebody might have found on Stack Overflow or GitHub and applying it in your product is the difference between these 2 instances of crypto you see depicted with the Linux Penguin there. On the far left, you see the unencrypted Linux Penguin. In the middle, you see the badly encrypted Linux Penguin, and you can still tell what it is because it's the Linux Penguin. And on your far right, you'll see that what a cryptographic picture should look like. Something that's been encrypted properly should be completely indistinguishable from noise. So this is a very classic example of using crypto wrong and actually completely weakening it. And this was the example that everyone was using that we found a few years ago. So developers are just not being set up for success in this sense. So we saw this situation and we built a string library. So hopefully if you perform that Google search today, you'll find this string library is actually the first hit you'll find. So we realized people wanted something that you could easily copy and paste, and we created this library that actually used AES correctly, and there was some weird nuances in Android that we fixed at the time. I think those are all addressed nowadays. So this is out there. We built this to help people, and it's out on GitHub and open source, and it's pretty widely used nowadays. So we find it in really surprising places and get funny bug reports about it. This work really inspired us to realize this challenge that for cryptographic tools for programmers. So let me take a step back and say why we think the problem exists in the first place. So if you're building a security system that uses cryptography, this is the abstraction stack that you have to deal with. So abstraction, all computer software is built on some kind of abstraction stack, right? So this is the one for cryptographic or security tools. On the far left, you have math. Then you have the algorithm, which is like AES, like I was just talking about. Then you have the library that implements that algorithm, which was that Java thing I showed you. Then you have the protocol. The protocol could be something like in this community like OAuth or OIDC. Then you have the library that implements that protocol. You have the applications actually trying to get a job done. And finally, you have the privacy and security goals all the way on the other side. So the problem is, even if you have tools for each one of these parts of the system, there are mistakes that creep in between the abstraction layers of the system. So if you get the math right, but you don't implement the algorithm according exactly to the math, then you get a mistake, and you get these kind of problems. So every single layer has this challenge. And for AES, the funny thing is you can have plain text, apply AES, and then you get something on the right-hand side that certainly looks encrypted if you just look at it, but unless you do an analysis of it, you realize it's not actually that secure. So there's the funny guy with the helmet there is just showing the helmet's not that useful if you're using it wrong. The bigger the gap, the bigger the conceptual gap between these layers, the bigger the mistakes the computer programmers are going to make. So most of the time we have very, very little support between layer 3 and layer 6. So the application library or the algorithm library that you're using, like that Java thing I showed you, to the application logic and the security goals of the system, there's just almost no tool support. Again, in a community like this, we have a lot of specific things to solve specific problems, like OAuth and OIDC, that would fit in this layer. If those don't happen to be exactly what you need, then you have to start from scratch. And it'd be nice to be able to push this boundary a little bit to the right. But of course, that's a nice opportunity for all of us to work and improve the situation. So let's talk a little bit more about our work with NIST that we performed to define a product to address this gap. So we started off with an understanding of developer need. More and more developers need to handle personally identifiable information. PII can mean kind of anything from email, phone, home address, medical information. It's really context specific. So in some environments, your name is very, very sensitive PII, like in a healthcare environment or all of Europe. And in other environments, these things aren't considered sensitive at all. Everybody wants to do the right thing. They want to protect that data. And we know that encryption is a very effective tool for protecting data. Most developers, or many developers, have some kind of regulatory requirement, and many don't. It really just depends. If you're in a semi-regulated industry like healthcare, you probably have some kind of requirement to protect this information, but you may be in social networking and not have any kind of requirement to protect this information. Europe is really pushing the envelope on this, as I was joking, because of the GDPR, a new privacy law that's coming into effect. But really importantly, especially when it comes to crypto, solutions here can't compromise business requirements. You need to process the data. You need to analyze the data. Almost everybody has this as part of their business nowadays. So we can't make it so the data is completely opaque all the time. You have to give the right parties the ability to decrypt the data. So the problem. So that's what you're trying to do. Here's why you can't do it. As I mentioned, developer tools for cryptography and security are terrible. You get this guidance that says never roll your own cryptography, and that's true. You don't roll your own AES. But AES itself doesn't solve the actual problem you have. It's not high enough in the abstraction stack to solve the problem you have. So you have to apply some best practices too. Security is really most effectively built into systems at the code level. Almost all security vulnerabilities are programmer mistakes. Now, if you wander around most security conferences, you'll see if you take the product development lifecycle with conception of the tool at one end and implementation and deployment and retirement, stuff is actually pretty far to the right. The stuff that you can buy for IT is pretty far to the right. We have VPNs that are deployed into a network after the software and everything has been developed and deployed. You have virus scanners that scan the systems, but very little further to the left-hand side that actually help computer programmers build these things. But the challenge is that the vulnerabilities you have are in SQL injection, are in cryptographic mistakes, are in all kinds of errors that computer programmers make. So how do we help them? The other challenge here, of course, is time to market, and this is really true of the IoT space, of course, because it's so exciting. Time to market is the top concern. Security is secondary, privacy is after that somewhere, and expectations for deliverables are always on the rise. So people want to get this thing to market, and they figure, well, if it's insecure, we'll fix it later. And this has been a huge, huge challenge for the whole industry for many years. So here was the solution we came up with, and I'll talk about how we applied NIST Framework to this solution. So it's an end-to-end encryption system. The idea is give a programmer the tool to collect and protect the data, to store it and to control it, and then analyze the data and empower the user whose information is represented by that data, I should say. So the idea, let's say, just take the web example. You take your front end HTML code, you add a few custom tags, and you basically tell it to encrypt the data in the browser. So this is really end-to-end, encrypted in the browser. Client-side SDK, starting in the browser, manages the keys and everything for you. That's a software development kit, sorry. Then it gets transmitted to the system and stored, encrypted at rest already. So then the policy engine lets you configure access based on your business needs. Does the user need to be able to see the data? Do they need to be able to control who gets the data after it's collected? Do they need to be able to control retention periods of the data? Or who's in charge of making those decisions? Is it the end user? Is it the business logic? So all of that's in the policy engine. And then you can decrypt and analyze the data just like you would with any type of system. So sometimes we call this model, we call it Stripe for personally identifiable information, because Stripe has done a fantastic job with making it easy to collect and use credit cards. And so most programmers don't have to actually touch the sensitive information on credit cards. And very, very often when you see security breaches, you see this funny thing where it says 500 million user records were compromised with name, address, phone number, email address, and your passwords, but no credit card information was compromised. And you have to say to yourself, what are you doing with the credit card information? Just do the same thing for everything else. Why is it? Because PCI compliance has actually done a good job in making people not want to touch that sensitive data of the credit cards. So we said, why don't we try to use a similar model for all this sensitive information, all this PII, encrypt it very early, don't put the sensitive information in all the systems, put the sensitive information in a central store, encrypted, stored securely, and give people the ability to download, decrypt, and process it only if they need to. So that's the basic approach. So what do we do to apply the NIST framework to this basic approach? You'll hear a lot more about NIST framework, the NIST Privacy Risk Assessment Methodology. NIST has many, many frameworks. So you'll hear a lot more about this at a later talk. I'm just going to give you a very, very brief introduction to how it was at least a year ago when we were using it. So there's these 6 basic steps to assessing privacy risk in a system. This is really inspired by all the processes that are around for assessing computer security risk in a system. So step 1, framing business objectives, meaning what are you actually trying to accomplish? Who needs to control the data? Who needs to hold it? Frame the organizational privacy governance. For instance, what requirements do you have around HIPAA compliance or PCI compliance, or what are the rules around handling this data? Assess the system design if you already have a system. Where does data go? Who controls it at what point of the process? Then assess the privacy risks. So say for different types of events that could happen to this data, what's the impact to privacy, not just security, if this data is breached? Design new privacy controls over that data. So beyond security, you could have privacy controls, for instance, that the user has to opt in, not opt out of sharing. And then monitor change over time. So that's the basic approach. I think you'll hear a lot more about this later. So I'll dig a little bit into something we did with our system on step 4, just to illustrate how you can apply this system in a real-life project. So for step 4, the process was to think about all the terrible things that could happen to the data and put them on a little pretty colored chart like this and watch out for the red ones in brief. So think about the terrible things. What are the data events that you're trying to accomplish? You want to store and retrieve encrypted data in our system. What are the problematic what are the problematic things that could happen to that data? What are all the horrible things that could happen? So you could lose, for instance, you could lose availability of that data. There's a lot of things that could happen. We're just focusing on availability for this particular example. And what that means is that the user lost control of the data. It's no longer available to them. And that could be, for instance, because of loss of an encryption key. So you've encrypted something, you've lost the key, now the data's gone. How do you select, then you select controls for addressing security and privacy concerns, and the control we selected in this case was user-to-user encryption of selected data. Then you just analyze that. What are the considerations around why you made those choices and what impact they may have? So we knew that this type of encryption would be very, very effective at ensuring privacy of the data. It would make the code significantly more complicated and expensive to maintain. And it's extremely difficult to trust users to actually maintain their keys, because if they lost their keys, they had a very severe impact to availability for loss of that data. So this whole analysis can boil down to, in this one instance, basically, can we trust users to encrypt their own data? They lose everything. They lose their phones, they lose their keys, they lose their passwords. If we choose strong crypto, then that data is gone. You lose the key, the data is just gone, if you've done a good job with crypto. So this presents a bit of a conundrum, and you have to choose which door you're going to go through, because this isn't the right thing for everybody. Some data is, like probably the photographs of your kids, is so precious that you would never want to lose it, but it's not something that you need to protect so carefully, because if somebody saw it, it would be a terrible thing. On the other hand, you have types of data where the sensitivity and privacy of that data is the most important thing. So you have to make a choice. Is increased availability so important, your data so important that you can't risk losing it, where if you lose a crypto key, that's very, very bad because users lose and forget everything. So the implications for the design of the system in that case are we have to provide a mechanism for account recovery. We have to build key backup into the system, but that really increases the attack surface. That makes us a party to the keys that the user is supposed to maintain, and that means we can be attacked to disclose the key, which is something we don't want. Then on the other side, you have increased privacy. Your data is so secret that you can't risk disclosing it versus can't risk losing it. this is the case where any access to that data by a third party is a very bad thing. You have huge data breaches in the news all the time. The implications of that are you have to encrypt the data unrecoverably. Then users have to accept the risk of loss of that data, whether that's the end user or whether that's the programmer delivering the system. And you just have an increased risk of data loss. You just have to accept that. So these are two very, very different use cases. And what's really great about the work that NIST did in the privacy risk assessment methodology is that it helps to surface these types of trade-offs. Without privacy analysis, these trade-offs wouldn't be obvious. The pros and cons here and the applicability to different systems would be much more difficult to talk about. And it helped to really surface new options in the design space. So we said we want to be able to solve this problem for both types of users. And so we gave developers the option to use unrecoverable keys. The developers can give their users the option to use unrecoverable keys. And each party provides the recovery options that are appropriate for their use case. So we found a nice path through this system, basically by giving good default behavior and good options for the right people. So I really think of the PRAM as a structure for high-quality discussions. It's at a level that the various parties that are working on your systems can really understand, whether that's the client and product people, whether that's privacy lawyers and policy implementers, security and crypto engineers, or just pure programmers, IT people, DevOps people. They can all use this structure to have the right conversation about where the data is going, how it's being controlled, and how it's being used. This surfaces areas for design trade-offs. No system can be perfect for everybody. So it helps highlight the areas where you have trade-offs, you have some tension, and you have to just make some decisions. And it really helped us in our project to make trade-offs and to allocate resources appropriately across the system. So again, back to this idea that mistakes creep into the gaps between the conceptual layers that you build software on top of. And again, at your far right-hand side, you have the privacy goals of the system. So I think we're trying to, and I think NIST is fighting the good fight here, to close that conceptual gap with good tools. And the PRAM is a really great tool for closing that conceptual gap between what your application's trying to accomplish and what are the privacy goals of your system. And we're working significantly to close the gap between what I'm showing here is layer 3 and layer 6 for computer programmers, which is a really common area of security and privacy failures and vulnerabilities. So the resulting system goals of this whole analysis, to kind of summarize a few things, is that we targeted the most powerful privacy features in a system, like using end-to-end encryption for a system. And this was with a lot of help and encouragement from NIST. We targeted the most significant conceptual gap that took all the way from the cryptographic library to the application logic. And we realized that that really meant targeting developers where they live. Try and give them tools to build these systems, not just build a tool that end users can use directly. Target them with an interface that feels very familiar with developers. So we've done many, many dozens of interviews with developers, showing them different interfaces and different ideas and getting their feedback on how to make this as usable and simple as possible. And then we put crypto as much as possible behind the scenes so the developers don't have to feel like they're using these algorithms like AES and looking at the kinds of documentation I showed you earlier up on the talk. They don't have to think at that level. They can think at the level of their application logic and the security and privacy needs of their system. So let me just close with a few brief words on privacy because we've been doing a lot of work, and I know NIST has been doing a lot of work and focus on this area. It's really important to understand, as with security, that privacy is not the default in any system. In security, most software is insecure by default. If you ever sat down to write a web server, anybody could do that today. You can go onto the internet and try something, try writing some web server or web service. You will find that you write a very insecure system. You will have SQL injections in your system unless you take specific actions to prevent SQL injections in your system. The same thing is true of privacy. Most software is not built to be privacy preserving by default, I'm sorry to say. In fact, the business model of the internet often pushes us in the opposite direction. But unlike security, there's really very little overriding business pressure to help privacy along. Now, security's been bad enough. For many, many years, we've been saying, boy, there's just no business pressure to make security important, but that's improving slowly over time as people have realized the terrible impact of all these security violations. But privacy is still not as focused on even as security is, and definitely not as focused on as time to market is. But I have to argue, and I hope you all agree, that privacy is really important for human dignity. And I like to think of it like this. Does privacy matter? If you do anything that someone would disapprove of, if you believe anything that anyone else would disagree with, or if you have anything that anyone else would want or want to take away from you, if you say anything that someone else would fight against, or if you are anything that you think someone else would hate, privacy matters. These things are important to who we are as human beings. So I understand privacy gets in the way. So most people think of privacy when you're implementing a system like the picture on the left-hand side, which is a little gate, a very ineffective gate. And if you have privacy rules, let's just drive around that gate as quickly as we can. And the tracks in the snow attest to the fact that this is a very insufficient way of thinking about it. But I like to think of privacy as actually a foundation that we can build things on top of, not a gate to get in our way. When you log into your email, you are performing a privacy action. You're logging into an account that has your information segregated from other people's information. The whole concept of email and many aspects of the internet are built on this idea of privacy and keeping different information separate. And we don't think of it as getting in the way. We think of it as that's how these systems work and that's how they should work. And we build better systems on top of them. So let's keep thinking of privacy as a foundation that we build good systems on top of and not something that we should just try to get around and build systems without considering it. So that's all I have for you today. I think I'm just about running on time to let you ask a question or two if you like. All right. Well, hearing none, thank you very much. Really appreciate it. And